All right, so now we're going to put everything we've learned about vectors to the test and use it to do some geometric vector proofs. So some prior knowledge for this would be introduction to vectors, the dot product, and collinearity, which we covered in other videos. Some of the key concepts we'll cover in this video is just a review of vector properties, vector proofs in 2 and 3 dimensions as well. So let's jump into it. Let's have a look at introduction at properties of vectors, because we're going to need these properties in order to do our proofs. So some key facts about parallel vectors. If you've got some positive real number k, the vector k a is in the same direction as a and has a magnitude of k multiplied by the magnitude of a. That just basically means you can scale some vector a up or down by k. And if it's negative ka, it would still have the same magnitude. It's just pointing in the opposite direction. So yeah, just sort of this idea of scalability of vectors, and then they're still parallel. We can also say that two non-zero vectors A and B are parallel if and only if B is a scalar multiple of A, where K is not equal to zero. Again, that should make sense. You go to some vector in space. A B is parallel only if it's a scalar multiple of A. Okay, remember, it doesn't matter where your vector is situated in space. If it's pointing in the same direction, then it's going to be parallel. So we also spoke about collinearity. So three distinct points A, B, and C are collinear if and only if vector AC is equal to a multiple of vector AB. Again, for some k not equal to zero. Okay, go back and have a look at the video on collinearity. Basically, it just means those 3 points are the same or on the same line. Okay, then we also know the dot product is going to be very important. So two non-zero vectors A and B are perpendicular only if the dot product between them is equal to zero. Not equal to the zero vector, just equal to zero. Because remember, the dot product gives us a number as the answer, right? And we also know that when we take the dot product between two vectors, we get the magnitude of that vector squared. I should say more carefully, when we take the dot product between two vectors that are the same vector, you get the magnitude of that vector squared. And that's just a consequence of the geometric interpretation of the dot product, which we spoke about before. Okay, and just this idea of linear combinations of independent vectors. So if you have vectors A and B that are linearly independent, that means they're not parallel, then this is what we can say. We say MA plus NB equals PA plus QB. This implies that M equals P and N equals Q. Okay, and that might seem like stating the obvious, but let's just sort of think about what's going on here. We've got two vectors that are linearly independent, which basically means they're not parallel. So, yeah, you get a situation where the coefficients must be equal to each other. And I think a way to maybe explain this better would be to look at linearly dependent vectors to show that that's not the case in that example. So let's have a look here. For linearly dependent vectors, the coefficients in a linear combination are not unique. Okay, so let's look. So let's imagine we've got some vector A that points in the coordinate 1, 2, and then we've got some vector B, which is 2 times A. So it's just going to be at the point 2, 4 again. So now these are linearly dependent, which means they're parallel, which means they're in sort of on the same line, right? Okay, now let's consider a linear combination of um, yeah, A and B. So let's say M times A plus N times B. If we were to do that, we would get this, and then if we scroll down here a little bit, if we were to substitute B equals 2A into this equation, we would get MA plus N multiplied by B, which is 2A. Okay, take out A, the vector A is a common vector, or common factor, and you get M plus 2N multiplied by A. Okay, this shows that any vector in the span of A and B is of the form M plus 2N multiplied by A. Okay, so what that means is you're stuck on the line, okay, because those two vectors are linearly dependent, so you can't get away from pointing in the direction of A, okay, because it's a M plus 2N multiplied by A is not going to get you off the line of the direction that A is pointing, because and the way we sort of technically say that, yeah, the span of A and B is of this form. Okay, so for example, if we had some vector v was equal to 3, 6, we can see that this vector can be written as, okay, if m was 3 and n was 0, we would have this, that vector v could be expressed as 3 times vector a, so it'd be 3, 6, plus 0 groups of vector b. So v would be 3a plus 0b. Or you could see that there would be another example, right? You could have m being 1 and n being 1. So if m is 1, m multiplied by a would be 1, 2, plus 2, 4. So it'd be v would be one group of a plus one group of b, vector b, and that would also give you the same vector v. So you can see the coefficients are not unique when the vectors are linearly dependent. Okay, but they are unique when a and b are linearly independent. So that's what we've sort of said here. Okay, so that's just a review of that idea of linear independence and dependence, but it's a very important idea, so I thought we'd better cover it. Okay, let's have a look at a proof of a vector proof in two dimensions. So let's imagine we've got a rhombus. Let's just remind ourselves what a rhombus is. So a rhombus is a quadrilateral. It's got four sides of the same length, and um, opposite angles are not necessarily equal. So a square would be an example of a rhombus, but not all squares, but not all rhombuses are squares. All right, so here's an example of a rhombus that shows the properties. You can see that all the side lengths are the same, but this angle and this angle are the same, and this one and this one are the same, but this one and this one aren't the same, right? So that's an example of a rhombus. Another interesting property of rhombi or rhombuses is that the perpendiculars intersect, the diagonals rather, the diagonals intersect at 90 degrees. So we're getting that situation going on. Okay, and then we can do a vector proof. So prove that the diagonals of a rhombus are perpendicular. So now we need to prove it, right? So here is our rhombus, O, A, B, C. Okay, and these are all vectors. Okay, let's break it down. So let's let this vector from O to A be vector A, and this vector from O to C be vector C. So we get this situation. Hopefully pretty straightforward so far. Okay, the diagonals of the rhombus are OB and AC. So OB, AC would be the diagonals of the rhombus. Okay, now it gets a little bit tricky, but you can see that OB is the addition of OC and CB. So if we add this vector to this vector, we get this diagonal vector OB. Okay, and similarly, OC plus CV, OC plus CV, OC plus OA. Oh yeah, okay. Because CB and OA are the same, we can say that that's the same thing. So OC plus OA gives us um, OB, right? And then so we can say that C plus A gives us OB. Okay, AC, let's think about this, would be AO plus OC if we went this way. So now it's AO, so we're going in the other direction. So it's AO plus OC. But this direction here would be negative A. So this becomes negative A plus C. Okay, so consider the dot product between OB and AC. Okay, so we're going to take the dot product between them. So we're going to take the dot product of C plus A with negative A plus C. So that gives us this thing here. Expanding things out a little bit gives you C dotted with C minus A dotted with A. Remember, in a previous video, we spoke about properties of the dot product. It is distributive, so we can apply the dot product just like multiplication. So you get this. And yeah, we know that the dot product between a vector and itself is just equal to the magnitude of that vector squared. So you get the magnitude of C squared minus the magnitude of A squared. Okay, and hopefully you're seeing where this is going. Since a rhombus has all four sides equal in length, we know that the magnitude of C equals the magnitude of A. So we know that this must equal 0 because these two numbers, these two magnitudes are the same. And so this implies that AC is perpendicular to OB. And so there is our proof that the diagonals of a rhombus are perpendicular using vectors. Okay, so I think it's a pretty nifty idea. And that's a vector proof in 2 dimensions. Let's have a look at a vector proof in 3 dimensions. This one's going to be a little bit trickier. I recommend maybe pausing the video, just having a read of this, because when I go through and explain it, I'm going to try and step it out. And I'm going to use this over here, but it might get a bit messy. It's hard to explain. In any case, pause the video, have a look. We're going to go from the top. Okay, so here's our question. Let the points A, B, C, and D be 4 points in space that do not lie in the same plane. Let M, N, P, Q be the midpoints of AB, BC, CD, DA, respectively. Relative to an origin O, denote the position vectors of points A, B, C, D, M, N, P, Q. By these, prove that M, N, P, Q is a parallelogram. Okay. What I'm going to do is I've put the points over here just so we can get a picture of what's going on. These are the points. These are linearly independent. And what we're going to do is we're just going to connect them. So AB, BC, CD, and CA. So let's do AB. And then we can do BC, CD, and then DA. Okay, and we get something that looks like this. Okay, and what we want to do is we want to prove that the midpoints of these, of all these line segments, give us will give us a parallelogram. So let's put that there. Let's call that M because the midpoint of AB is M. Let's find the midpoint of this one. Let's again rename it. Let's call that N. Midpoint of this one. Let's rename that as well. We're going to call that P. And lastly, Q. So now I've got the midpoints of all those line segments. And basically, our job is to show that the shape that we get here, yeah, that MNPQ is a parallelogram. You can already tell it looks like a rectangle, doesn't it? And a rectangle is a parallelogram. Parallelogram just has opposite sides that are parallel. So that's looking pretty promising, but I suppose our job is to prove it. So what we can do is, yeah, let's prove it. So we need to show that opposite sides are parallel. Okay, and this is where it gets a bit tricky. So vector MN. Okay, MN is the vector that goes from here to here, right? Goes from the point M to the point N. Okay, that's equal to N minus M. Now that can even be tricky to wrap our head around. Remember, all these lowercase letters are from the origin to those points. So what we're going to do is we're actually going to come over here and get behind the scenes. And what we can do is we can make those vectors. So let's make a vector N that goes from 0, goes from the origin, which is at 0, to the point N. And now you can see we've got that there. Okay, then we can also make another one, make another vector that goes from O to the point M. Okay, and maybe to you it's obvious that N minus M is equal to this vector here, but to me it's not. So I need to sort of show that. So we've got these two vectors pointing at M and N. What we want to do is, yeah, just sort of confirm that N minus M is that. So in this case here, U has been defined as N and V has been defined as M. So if we do U, we should work if we do U minus V. Okay, and it's not perfect, but you can see that this vector here would go from M to N. And if you're not convinced, that vector is now called W. So we can call that vector start point. Let's start it at the point M. And then we're going to add it to the end of M. So it's going to be M plus W now. And you can see this now has an arrowhead on it. So that is in fact what we were after. So N minus M, just in case, it wasn't obvious to you because it wasn't obvious to me. N minus M is this vector from here to here. Okay, but we know that vector N, we should say we know that the point N is at the midpoint of B and C. Okay, so I'm hoping it's not too much of a leap to make the following claim, which is that vector N is vector B, which would be the vector from the origin to the point B, plus the vector from the origin to the point C, add them together, and then half of it would be the vector that points at the point N, right? Okay, minus N, sorry, minus M. So that's going to be the same thing. That's going to be a vector pointing at the point M, right? Because that's halfway between points A and B. And so, yeah, vector Mn can be expressed in this format. Okay, the same thing is true of vector PQ. PQ is this vector here, right? It's going to go from P to Q. Okay, and by the same logic, you're going to get this situation going on here. Okay, the vector from P to Q is Q minus P, just by the same reasoning. And so we get this situation. And then what we can say is the following. So the vectors for the opposite sides. So we know that Mn is equal to this if we just collect the numerators and then cancel out the b's, we'll get C minus A on 2 for Mn. And then for vector PQ, we get A minus C on 2 for the same reasoning, right? And so you can see that these are the same in size, but the opposite in sign. So they're the same size, but they're the opposite in sign, which means that they are parallel because if you've just got the sign swapped for a vector, then it's parallel. So we can say, excuse me, since vector Mn is equal to vector PQ negated, these vectors are parallel and equal in length. Okay? And since both conditions hold, MnPQ is a parallelogram. Now this is my solution. I wonder what you think, whether that's satisfactory. I think I might have missed the fact, in terms of the proof, that vector NP and vector MQ are parallel. Because I think what I've shown here might only satisfy the conditions for it being a trapezium. Because we've shown that one set of sides is parallel. And I think to show that it's a parallelogram, we would need to show that both sets are parallel. But I think with that logic, we could just do the same thing for vector NP and vector QM and show that they're parallel by the exact same reasoning. So I don't have solutions for this, so interested to see what you think, whether that's a satisfactory proof. Let me know if you think it is, but I think you can sort of clearly see anyway that you do in fact get a parallelogram when you sort of have these conditions. And I think that's pretty interesting. You pick 4 random points in space, connect them, and then connect the midpoints of all of them, and you get a parallelogram. Doesn't seem that that would necessarily be true, but seems to be the case. So such is life. All right. Hopefully you found that somewhat useful. Good luck with everything you're doing. And if you found it helpful at all, give us a thumbs up and subscribe, and I'll talk to you soon.